Okay, so for now we'll be talking about chapter 10, no? And after chapter 8, which is Alkanes, chapter 8 in Solomon's, our reference material is chapter 9, which is about NMR. We can learn NMR in higher organic chemistry, I think, kung na-accomation natin organic chemistry. So for now, we'll proceed with all the reactions, and that will be another kind of reactions, which is radical reactions. So in this chapter, we will consider the properties of radicals, their formation, and the reactivity, of course, the mechanism behind. We'll also be talking about that one, and then the significant radical-based reactions in nature. And then we'll also learn what are the starting materials. Now, what are the usual organic compounds that will undergo radical reactions? Okay. So far what we have learned, almost reactions as mechanisms in studies have been ionic reactions, right? There was a lot of questions actually in the exam, that the SN1 and SN2, and I wanted to ask that over and over again. I don't want you to forget about that one, because even after your chemistry program, your board exam, gawas pinang SN1 and SN2. And always have to remember that by heart. Say difference nila, and there are still some people na nakalimutan. So far we had been dealing with ionic reactions. Those are kind of reaction in which bonding changes occur with heterolysis. Sa heterolysis when there is bond breaking between two atoms. Now one of the atoms carries all the electrons. That is called an heterolysis bond cleavage. So when we form these ones, we form ions. For example, we form carbocation ions, we form carbanion ions. And we have always the kanina. Another broad category of reactions is mechanisms where bonding changes occur with homolysis. And some ng homolysis na may kayo ako. Ang homolysis is homolytic bond cleavage. Unsa nang homolytic kanang kasabot nga one of the reactants or both of the atoms in a bond would take one electron for each, and we call that one unpaired electrons as free radicals. Or radicals, so unsa man na siya? For example, nakay two atoms bonded to each other by a covalent bond. For example, when you do homolysis, or homolytic bond cleavage, each atom will take one electron from the covalent bond. That each atom will actually obtain an unpaired electron. Always in the heterolytic bond cleavage, the electrons are always paired, but in the homolytic bond cleavage, the electrons are unpaired. So when the electrons are unpaired, we call them as radicals or free radicals. So how do we produce radicals? So we can produce energy in the form of heat or light must be supplied to cause the homolysis or homolytic bond cleavage. So what is our source of free radicals? Usually we have our peroxide. So manang peroxide, kanang naakay OO bonded to each other, and then pending na kung ang alkyl groups are attached to your oxygen. So you have your dialkyl peroxide, and then in the presence of heat, the covalent bond between the two oxygen atoms, ma-distribute na siya sa duha ka oxygen atoms. So if you have your 2,4, dapat kung ma-cleave ni siya, kaning covalent bond, represented by two dots here, the covalent bond between the two oxygens. It undergoes homolysis, one of the oxygen or both oxygen will take one electron pair. Okay, so instead of 246, 246 nga unshared electrons, na lang kay 5, and then of course a bond with another atom here. So 246, 7 actually electrons that surrounds your atom, so it's unpaired. And since it's similar na siya nga R, we actually produce two alkoxy radicals. So that is our main source, or dialkyl peroxide. And another source will be from halogens, kanang X2, The halogens contain a relatively weak bond. By the way, the OO bond is mentioned because they are both electronegative. All the Nganong weak man siya, this OO bond, oxygen-oxygen bond is actually weak. And nganong weak na siya, if you remember, both of the atoms are electronegative. So if they are, for example, sharing electrons with each other, no, both of the atoms will actually draw electrons to itself, no, so that the bond actually between the two is very weak. That in the presence of heat, we can actually break that bond to produce our radicals. In the same way, when you have your halogens, just like your oxygen can also be like an electronegative atom. It also has a high electronegativity. For example, your Cl2, there would be the Cl is a very electronegative atom. So the XX bond or the halogen-halogen bond also is relatively weak bond in such a way that in the presence of heat or light, okay, Hb can break the halogen-halogen bond to form a radical. So if you see here an unshared electron here, two stars, so you have your kato, X2 and your peroxide. So almost all small radicals are short-lived and highly reactive species. So once we produce this, once you produce our radicals, actually, those radicals are actually short-lived and they are very highly reactive. So in such a way that they will seek another atom to pair with its electron. Okay, so when radicals collide with other molecules, they tend to react in a way that leads to the pairing of their unpaired electrons. So since unpaired na siya, no, that is the reason why it becomes very reactive. It always seeks other molecules, seeks to collide with other molecules to have a pair of electrons. No? And one way they can do this is by abstracting an atom from another molecule. To abstract an atom means to remove an atom by homolytic bond cleavage. So you have an unpaired electron here, no? And when they collide with another atom, since isa naman ka electron ang iyang kailangan, no? And the other molecule from another atom will also need to form a radical for an electron. So for example, if you have a halogen atom, you abstract a hydrogen from an alkane and by homolytic bond cleavage. So example, you have already your radical, and if for example you have your alkane, with the hydrogen here, okay, they can abstract the hydrogen from the alkane to form a bond. So it can be neutralized here. Okay, it can be stabilized. The radicals being formed can be stabilized by forming a bond with another atom from another molecule by homolytic bond formation also. So it can abstract the one electron from the other molecule. Okay, for example here hydrogen by homolytic cleavage, and ang isa ka electron mabelong madto ra gyapon sa molecule, and in the end you also produce another radical in the process. So you call this one as hydrogen abstraction. So in this hydrogen abstraction, it gives the halogen atom an electron from the hydrogen atom from an alkane, for instance. So however, the other product is another radical. So I mentioned this one. You can actually produce another radical. So this is a general mechanism for the reaction we call hydrogen atom abstraction. You have your radical, starting radical. Of course, you already know how to have your radical here. You start with X2, katong X2 ni more halogen in the presence of heat or light. You can produce this one. So there should be another one here. And after that one, you react with, it seeks another molecule to form a bond, kaya reactive man siya kayo, and you form another radical. So let's have a specific example. For example, you have your chlorine dot, no? Can the chlorine radical here can abstract the hydrogen from another alkane, from an alkane, for instance, since the alkane usually, the hydrogen carbon bond is also a weak bond here, and can easily abstract that one. You can have your HCl and produce another alkyl radical here. You can also, your radical can also seek, aside from an alkane, no, an alkane can also seek to form a bond with an alkene, no, by again homolytic bond formation. So if you have this one, you can form your R6, one electron here from your double bonds. It will utilize the electrons from the pi electrons. So you have your R and you have two bonds here, and you have R and C formation, okay, and by one electron from carbon, and then you have your bond here, bond, and since one of the electrons is used to form a bond here, the other will go to another carbon dot, no, a radical, another radical, and then this bond here. Okay, so there are two ways for the radical to seek another molecule to form a bond. You can form a bond with alkene, or you can form a bond with alkane. And so you can read this one, the chemistry of acne medications. Now it uses benzoyl peroxide. It turns out that although certain peroxides are great at initiating radical reactions, peroxide radicals also have many valuable uses on their own. For example, benzoyl peroxide is an active ingredient found in many acne medications. You can look at your personal care products. Not every time you purchase your products, and since you have already a background in organic chemistry, you can always check on the labels, and even sa kanang upuan, as in yung mga labels, no, you always have this one. Benzoyl peroxide can also find that one sa kanang antiseptic materials kana sa mga hospital. Okay. So here is an example of benzoyl peroxide, which used as an active ingredient in acne medication, no, that breaks apart and form radicals through the warmth for skin exposure to light. So nga ginagamit man ni siya, these radicals, of course, you can see here your OO. Okay, can easily break, can easily produce your radicals here. Once you have your radicals, these radicals can kill the bacteria that causes breakout. So this one will react with the proteins and amino acids and surface of the bacteria, no, to bind sa mga bacteria and surfaces so that it couldn't infect na sa mga skins. So the same compound also used as a whitening and bleaching agent. You can also find this in mga hypochlorite, you know, all sorts of radicals. As in the chapter 13, many colored compounds, and the benzoyl peroxide can also add to those bonds, break conjugation, and remove their color to leave behind new white materials. So they are used as also whitening agents. No? It reacts with other materials to form a bond. Again, the reaction will be similar to like this. No, once you produce your radicals OR, you actually initiate the radical reactions. So let's talk about the homolytic bond dissociation energies. Now, when atoms combine to form molecules, like you have your dot hydrogen, what happens is that when they form a bond by homolytic bond formation like this, these molecules are products of lower enthalpy than the separate atoms than this one. Okay, so you actually have the bond formation in this process to be an exothermic process. Energy is being released when bond is being formed here. So when a hydrogen atom combines to form hydrogen molecules, again, the reaction is exothermic, and this is for hydrogen. Also, when you see for chlorine, the reaction is also exothermic. And you have here, you can see the delta H. You have your physical chemistry, right? So we understand this delta H, standard enthalpy of formation, standard enthalpy for this reaction. You have here to be negative, and that means it's an exothermic process. And if you do the bond breaking, homolytic bond breaking process, the process is the opposite. No, it is an endothermic process. Instead of negative, energy is being absorbed. No? So when we need to break this bond, you have, of course, to absorb a certain amount of energy to have your radicals form. And again, this process for homolytic bond cleavage is an endothermic process. And this is opposite to what you can see in the bond formation, which is exothermic. No? So energy must be supplied to break covalent bonds like this one. Okay, and that's why it needs to absorb a certain amount of energy. And the energies required to break covalent bonds homolytically are called homolytic bond dissociation energies. Since this one is homolytic bond cleavage, you call this one, the energy associated with this is called as homolytic bond dissociation energies. And they are usually abbreviated as delta. Okay. So, and the homolytic bond dissociation energies of hydrogen and chlorine, for example, can be written as IDH dissociation energy, sorry. DH, dissociation energy. Dissociation bond energy. It's you have this pagkani. It's also abbreviated. The delta H can also be named as DH. You have your DH. You have your, okay, it's different from other books. No? So you have here the homolytic bond dissociation energy. You have the same way for different molecules. No? So again, this one is an endothermic process. So let's see how to use the homolytic bond dissociation energies to determine the relative stability. So again, we can use the bond dissociation energies to know the relative stabilities of our radicals based from our, for example, starting organic compound. Let's say here, starting material is our alkane. Okay, this one you have your 1, 2, 3. This is propane, 1, 2, 3. This is also propane. But when you do homolytic bond cleavage, depending kung asang hydrogen atong i-dissociate, no? And asang carbon hydrogen atong i-dissociate, no? The relative stability, the radicals that is being formed in the process of dissociating the carbon hydrogen, depende siya kung unsa nga type na radical is being produced, no? So we can actually produce a primary radical, 1 degree, 2 degree, or a 3 degree radical. So for example, if you dissociate kaning terminal carbon, hydrogen, okay, what we actually produce is a propyl radical. So when you have this one, you have your propyl radical, and the dissociation bond energy is positive 43 kilojoules per mole. And if we dissociate kaning sa middle ng carbon, second carbon hydrogen bond to produce our radical here. This is again our 2 degree radical. So there is this carbon here, you have a dot, you have a radical, and there are 2 alkyl groups attached to your carbon radical. So this one is a 2 degree radical or secondary radical. This one is a primary radical. You have your carbon here and carbon dot, carbon radical, and on this carbon there is one alkyl group attached to it. So this is a 1 degree radical. And you noticed here that the bond dissociation energy is different, even if they have the same starting material. You have your propane, no? And here we can actually estimate or can use the bond dissociation energy to determine the relative stabilities of our radical. Here, you have here, this one is much lower. The delta H is much lower for an isopropyl radical. It's being formed in the process. And your propyl radical is a delta H, which is much higher, by 10 kilojoules per mole. And so you can think which of the two would be more stable. Of course, you choose the one that would have a lower delta H. This one, the 2 degree radical, the isopropyl radical, actually is a more stable radical than this one, based from the bond dissociation energy. Okay, so the lower the bond dissociation energy, the more stable is your radical to be. Okay, and so here is a table for a single bond homolytic dissociation energy. You have a list, no, from hydrogen to halogens to hydrogen halides to your alkyl halides, alkanes, alkyl halides, ether, alkane, alkyl halides, and increase the number of carbons, and then more R groups attached. And then when the red one is the one that you have to dissociate by homolytic cleavage, produce your AB, from AB produce your A dot B dot. Okay, you produce here your, for example, you produce here is H2 dot, and the other one is hydrogen dot. So there is this bond dissociation energy, and you notice, let's see here, the lower your bond dissociation energy, DH, no, note, you can have a more stable radical that's being formed. And you notice here, for example, HF, HCl, HBr, HI, produce I dot, Br dot, Cl dot, F dot. The more polarizable is your atom. You notice that the lower is the bond dissociation energy here. The same way here, you have your CH3F, CH3H, mas CH3F, Cl. Paingon diri, maklaro ba akong slides, no? Magkagamay ang imuhang bond dissociation energy, and that will be an indicator that the radical that's being formed from this process, the I dot, no, is actually more stable. So here in the process, you actually produce CH3 dot, the same na siya, no? But the other dot, the other radical, you actually produce H dot, F dot, Cl dot, Pr dot, I dot, no? And there you can see that the other radical actually is much more stable. Fluorine dot, I dot is much more stable than Br dot, Cl dot, or F dot radical. Okay, so the same thing here. You can see the trend is much similar. So next. For the homolytic bond dissociation energies, we can use the table, no? Reactions resemble in each other in two respects. They both begin with the same alkane or propane, or they both produce an alkyl radical and hydrogen atom. Now, if you have your here, you have your, let's say, alkane, start with alkane. You have start with alkane. Let's see. Katong kanirang pasabot kan the same alkane. Sa tanan ni gipakita niyo kanirang alkane. They start with the same alkane. They differ, however, in the amount of energy required and the type of current. I've already mentioned they actually produce different kind of radicals. So just a note that more energy must be supplied to produce a primary alkyl radical. Kani, the propyl. Kani, you have more energy that's being used to produce your propyl radical than your isopropyl radical. And in the process, this means that the primary radical has absorbed more energy and there's a greater potential energy. And because of that, the relative stability of chemical species is inversely related to its potential energy. So you have a greater delta H, no? Bond dissociation energy, it means that there is a greater potential energy, and it means that the stability is inversely proportional. And we have mentioned it. So here we can use, and the reason why I've shown the data, you can also refer to the table for the data of the bond dissociation energies for most organic compounds. No? You can use that one to have a comparison. For example, you have your third butyl radical and isobutyl radical relative to your isobutane. You can find it there for the isobutane. And for a 3-degree radical, again, for example, you have your, earlier we have an example sa to propane, no, itong example. Here we have another example for isobutane. So we can use the table that we have shown earlier as a comparison, no, for our 3-degree radical, and if you have a 1-degree radical. So depending on siya, for example, you have carbon, 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 4 carbons. If you break the bond here, you produce your isobutyl radical. If you break this bond here, to produce this radical, you have your third butyl radical. And you notice on the delta H condensation energy between these two kinds of radical. One is you produce a 1-degree radical, the other is a 3-degree radical. And you notice that for a 1-degree radical, no, the delta H condensation energy is high, more passively positive. No, it means that there is a very high potential energy. And the stability is inversely proportional to the potential energy, delta H. The bond dissociation energy as compared to the 3-degree radicals. You can say that the 1-degree radical here is much less stable than the 3-degree radical based on the dissociation bond energy. And here is a potential energy diagram for the you have your propyl radical here from your propyl radical, and this one is letter B, third butyl radical. So the one that we have, the first example, this is the potential energy. And here you have your 423, the potential energy is much higher, obtained from your 1-degree radical. And the other one is you have 413 kilojoules per mole obtained from a 2-degree radical. And for the last one, kani, radical, you can see that the 3-degree radical has a lower potential energy or a lower delta H bond dissociation energy than that of a 1-degree radical. So again, your delta H is akin to your potential energy. The higher your potential energy, okay, the higher the value, the less stable is your radical. And the lower the value, the more stable is your radical. In fact, we can have the relative stabilities of radicals. A 3-degree is much more stable. 3-degree is much more, 3-degree radical is much more stable than a 2-degree radical, than a primary radical, and a methyl radical. So the stability actually is the same as that of our carbocations. So all the radicals are uncharged. The carbons that bears an odd electron is electron deficient. You can see here. And so we can stabilize. The reason for the stability of the 3-degree radical and 3-degree carbocation and 2-degree carbocations compared to the other is the same reason that the stability, the trend for stability of the radicals is the same as that of the carbocations. So even if you don't see a positive charge on the carbon, but there is an electron dot here, it's still electron deficient. So any alkyl group, no, that could donate electrons to your carbon could stabilize your radical, your carbon that has the radical that is unpaired. So any way, any alkyl groups that can donate by electron inductive effect can actually stabilize our radical. So again, the reason for this is the stabilizing effect due to hyperconjugation and katong hyperconjugation and sabtong hyperconjugation kanang kay carbon hydrogen. Here you have an sp2 hybrid orbital for your carbon, and you have your sp3 hybrid orbital here. The carbon hydrogen utilizes an sp3s bond, and this one utilizes an sp2 bond. So here there is a vacant p orbital, and you have an sp3 orbital here, and you can stabilize this one by like sideways overlap. No, it's called hyperconjugation. And another way is by electron donating inductive effect. Again, there are 2 ways to stabilize our radicals and our carbocations. We call that one as hyperconjugation, and the other one as electron donating inductive effect. So the more alkyl groups, the more stable is your radical. And the reasons, again, the reasons for stability of radicals and carbocations are similar. So I have to add here that there are 2 ways to stabilize your carbocations and radicals. You have the hyperconjugation, and you have an electron donating Inductive effect. To stabilize the carbocation, and radicals. So you have your factors, you have your hyperconjugation, you have the electron, due to the CH adjacent. Okay, you have the sp3s CH bond. Kanang silingan niya, no? And you have the electron donating inductive effect. Induced lang siya by the alkyl groups, by the adjacent, one of the adjacent alkyl groups. And the other one actually is wala pa diri, no? Whenever makasilingan na si carbocation og pi electrons. The other one is pi electron. I don't know nga wala pa nag-discuss si pangalan niya, si Solomon's. Pi electron delocalization by the adjacent C, whenever you have C double bond. Okay. Okay. I have no klaro ninyo, no? So do not forget these reasons to stabilize our carbocations. It's the same reason that we stabilize our radicals, no? So far, we haven't had an example of our carbocation adjacent or silingan sa double bond. Usually, we only have a carbocation na silingan ang alkyl. No? So you have your alkyl, it can be stabilized by hyperconjugation effect. Katong mura siya mo sideways overlap lagi, no? Sa sp3 and the vacant and the p orbital. With the adjacent sp3 is in bond and p orbital of C dot or C plus carbocation. Grabe na siya na. Explanation. Anyway. Balik-balik ring explanation. The other one is electron donating inductive effect. The other is the pi electron delocalization whenever you have an adjacent single bond C. So for example, ang silingan niya kani si carbon, yan na siya double bond carbon or nakay ring here katong sa nga ring sa aromatic ring kang benzene ring. So mas stabilize siya ka ma-appeal man siya si radical sa stabilization, sa electron delocalization, and you can actually do resonance structure for that. And you can actually apply, propose a resonance structure whenever you have a carbon dot or a carbon plus, you know, with a resonance effect. Okay. So problem before we end. Classify each of the following radicals being 1 degree, 2 degree, and 3 degree, and rank. Now I answer and rank them in the order of decreasing stability. So which one is more stable here? So wala pa nakabantay. Letter A, the most stable rather. Letter A, letter B, letter C. Donna. There are 3 radicals here. The most stable radical is Donna. By the way, ha? Letter
B.
Sunod.
Letter B.
Sunod.
Letter A.
Sunod.
C. Dionysus.
Of course, letter C. Okay. Ano man yun? I remember now, there is one. Si Rachel. Na si Rachel?
Yes, ma'am. Hello.
Ikaw man siguro itong nag-message ko, Rachel, no?
Yes po, ma'am. Ako to, ma'am.
Yun sa man to nimo. Ano naman ko, eh? Okay, balik ko sa sinugdanan na itong anong, wala ni mo na-submit, no, Rachel? Naka-remember rin na ito.
Ma'am, wala na. Ay.
Okay, later, we'll talk Rachel na. So, let's have continue with our lesson. Time check. So, 5 minutes copying. So, anyway, this is the same problem. Let's proceed on the reactions of alkanes with halogens. No? So, alkanes react with halogens. So before we end, proceed to test our reactions and the mechanisms. And Rachel, we can talk after that session. So again, so alkanes can react with halogens by radical halogenation. Remember your alkene, double bond, C double bond, C reacts with halogens by addition reaction.